you already know the addition of matrices and multiplication of matrices. Next comes a definition, transpose of a matrix, say matrix A, given is a matrix A. Then what do you mean by transpose of matrix A? So the transpose of matrix A is obtained by interchanging the rows and columns of A is called transpose of A and is denoted by A dash. Transpose of matrix A is denoted by A dash. Theoretically speaking, if I say that matrix A is denoted by Aij m by n, that is, that the matrix A is of order m by n, then its transpose, that is A dash, will be Aj of order n by m. That is, the transpose of matrix, the order interchanges. Let me take an example. Let's take an example to illustrate you what is transpose of a matrix. Say given is a matrix A, 2, 3, 5, 4, 0, minus 1. What is the order of this matrix? 2 by 3, 2 rows and 3 columns. So what is transpose of this matrix A? I should write symbol A dash here. A dash equal to, interchange the rows and columns. What are the elements of first row? 2, 3, 5. So you write this 2, 3, 5 in the first column, 2, 3, 5, and 4, 0, negative 1 in the second column. So that way the transpose of matrix A, that is A dash, is 2, 4, 3, 0, 5, minus 1. And what is the order of it? Order of it is clearly 3 rows and 2 columns. So that's how we define the transpose of a matrix. Now the next is properties of transpose of matrices. Properties of transpose of a matrix. What are the properties? The first property is that the transpose of a matrix is the matrix itself. The second property is, if you have a matrix K times A, K is a real number, so if you have a scalar multiplication Ka, then the transpose of Ka will be K remains as such multiplied by its transpose, that is Ka dash. Now the third property is the transpose of sum or difference of two matrices. Let A and B are two matrices, then A plus B dash will be A dash plus B dash. That is, the transpose of sum of two matrices remains the same as their sum of their separate transposes. And when I write plus minus, that means if it is sum on the left, it will remain sum on the right. If we have A minus B, then on the right side also it will be A dash minus B dash. Now the fourth and the last property is the transpose of product of two matrices is equal to the product of their transposes, but in the reverse order. It is very important to note that AB dash equal to B dash into A dash. And all these properties in the exercise will verify with the help of examples. Now the next is, we define a new definition, symmetric matrix. When is a matrix said to be symmetric? Symmetric matrix. A squared matrix A. So please note that for a matrix to be symmetric, the first required condition is it should be a squared matrix. So I define a squared matrix, say A, a squared matrix A. Let us define A equal to Aij and of course the order will be n by n, this being a squared matrix, is said to be symmetric if the transpose of A is same as A. Or in other words, Aij equal to Aji for all I and j. Let's take an example. For example, if I define matrix A as -5, 1, 3 and 1, 7, 2, 3, 2, 10, what is the order of this matrix? 3 by 3. So it is already a squared matrix. Now let's take the transpose. What will be A dash? Write the elements of first row in the first column, -5, 1, 3. That of second row, 1, 7, 2 in the second column. And the third row, that is 3, 2, 10 in the third column. And again it is a matrix of order 3 by 3. And what do you find? That the matrix remains exact the same. Here we find that A dash is same as A. So we can conclude that the given matrix A is a symmetric matrix. Now next definition, what is a skew symmetric matrix? What is a skew symmetric matrix? Again, like in case of symmetric, it has to be a squared matrix. So a matrix, a squared matrix A, let us define A as Aij, an order of order n or n by n, so it is a squared matrix, is said to be skew symmetric if A dash equal to negative A. Or in other words, if Aij equal to negative times Aj for all I and j. Now here, please make a note that when it is true for all I and j, that Aij equal to minus ji, what about when I equal to j? That is the diagonal element. Then Aii equal to minus Aii, that is the diagonal elements are negative of itself. Is there any real number which is negative of itself? It is only possibility 0. Because 5 is not equal to negative 5, it is 0 or negative 0, doesn't make a difference. So please note here, before I take an example, that all diagonal elements of a skew matrix are 0. All the diagonal elements are 0. And now let me take an example. Let's take a matrix A defined as 0, -1, 5, 1, 0, 4 and -5, -4, 0. What is the order of this matrix? It is a matrix, squared matrix of order, say, 3 by 3. What is A dash? Find out the transpose. The elements of first row should be written in the first column, 0, -1, 5. Then second row, 1, 0, 4 you write in the second column. -5, -4, 0 you write in the third column. Take a negative sign common throughout. So it may be written as negative common means multiplying or divide each element by negative. 1 you get 0, -1, 5 and you get 1, 0, 4 and you get -5, -4, 0. Isn't it same as the given matrix A? So you get A dash equal to -A and hence the given matrix A is a skew symmetric matrix. So that is about skew symmetric matrix. Let us have a theorem based on symmetric and skew symmetric matrix. Call it theorem 1. Note down the statement. For any squared matrix for any squared matrix A with real entities, number one, the sum of matrix plus its transpose is symmetric. The sum of a matrix with its transpose is symmetric, but the difference, that is A minus A dash, is always skew symmetric. It is easy to prove it. Let's take the proof of the first part, that let P denotes A plus A dash. We want to prove that P is a symmetric matrix. It will be so if I get P dash is same as P. So now we consider P equal to A plus A dash, and now consider P dash. So P dash will be A plus A dash dash. Now you know A plus B dash is A dash plus B dash property. So using that it will be A dash plus A dash dash. Then further you know the property that A dash dash is same as A. You also know that the addition of matrices is symmetric. So addition of matrices is commutative. So it may be written as A plus A dash. And now if you look at 1, where we let me call it 1, from 1, A plus A dash may be replaced by P. So what do you finally get? That the matrix, if there is a matrix P given as A plus A dash, then its transpose P dash is same as P, or in other words, P is a symmetric matrix and P is nothing but A plus A dash is a symmetric matrix. And now let us take the second part. In the second part, we denote let Q equal to A minus A dash, and then which implies Q dash will be A minus A dash whole dash. Again, you know the transpose of the difference. Also observe that it will be A dash minus A dash dash. And you know A dash dash is same as A. Take negative common, you get negative times A minus A dash, and which is as per definition being denoted by Q. So what do you find finally? That Q dash is negative Q, or we can conclude that Q is a skew symmetric matrix. And what is Q actually? Q we let as Q was nothing but A minus A dash. So A minus A dash is a skew symmetric matrix. Now theorem 2. The theorem 2 again regarding a symmetric matrix and skew symmetric matrix. Please note down, a squared matrix can be expressed as sum of a symmetric and a skew symmetric matrix. A squared matrix can be expressed as, say, A can be expressed as P plus Q, where P is a symmetric matrix and Q is a skew symmetric matrix. And it will be easy to see that A can be expressed as half A plus A dash and plus half A minus A dash. And you already know that here this, if I denote this half A plus A dash by P and half A minus A dash as Q, it will be easier to prove that P is symmetric and Q is skew symmetric, and that is the result.